Newton's method is an effective way to compute a root to certain equations or a root to certain functions. The idea of Newton's method is you put a point near the root to the function f, okay? Then plot the tangent line, then the tangent line intersect at the x-axis at another point, and then at this intersection you lift it upstairs on the curve and plot the tangent line again, so etc., etc. So if for a reasonable function, then you get a sequence of numbers that converges to the root of the function or converges to the root of the equation. Now, to unravel this algorithm, you finally, what you finally need to do is you iteration this function. Let me make it this bigger. What you finally need to do is you iterate this equation for some initial value. Okay, your initial value should be reasonable near the root. Okay, then in this situation, then you get a really good algorithm converts fast to the root. Okay.
Timing.
Any question?
这应该还上节课了。
X1 is x1 minus.
Okay, so x1. So what we do is x1. You choose x1 to your point near the root. Okay. Then what you do is x2. X2 is hxy, and x3 is hx2. Here h is our function. Here h is hx. You plug in x to the function h is x minus fx over f derivative. Yeah. So from you choose a point near the root x0. You choose x1, and then you plug in to the function h, and then the function value output gives you the new x value. Okay, and then you put this new x value to h again. Okay, so you get a x3. So plugging x3 to the function h, then you get x4, etc., etc. So this gives you a sequence. This gives you the sequence. This sequence, if the function is reasonable, then this sequence converges. You see, this thing converges to a desired root. Okay, to a desired root. This is the example that we did last time. Let me see the example. Okay, then let's see some other example. For instance, let's do an example. Let's see this example. X power 4 plus x. Let's see, minus 4 is 0. Find the root. Find the root. Okay, as I mentioned last time, degree 3, degree 4, we have similar solutions, like formula of these solutions, like the quadratic. I think degree 3, degree 4. Degree 3, the solution, the formula is still reasonable, and degree 4 turns out to be really hard to write it down. You know, there's a formula, but it's hard to write. Algebra is heavy to write it down. So in theory, it can be solved by this algebra, by radical. But in general, if you have degree 5, degree higher than 5, a polynomial, in general, you cannot solve it by radical. This is a famous problem in mathematics that proved by Abel and Galois. This one, actually, you can use this formula. However, we will try to solve it numerically by Newton method. Okay, first we construct the function f. By fx be okay. let fx be the thing, be x power 4 plus x minus 4. Okay, then you use so here fx is continuous, then fx is continuous. So then you check its function value at 0 is -4 less than 0. Now its function value at 2, which is 16 plus 2 minus 4, so it's 14 positive. So then by the continuity, if you plot of continuous function at 0 it's negative function value, and then at 2 it's positive function value. Now if you plot a function, reasonable function continuous, then you see by continuity, by intermediate value theorem, there exists a root x0. Okay, i.e. fx0 equals 0. Okay, which gives a solution to this, implies x0 is a solution, has a solution x0. Now we find this solution numerically by Newton method. Okay. Okay, let's use Newton method. Then we should iteration to this. Use this iteration. So hx be x minus fx over f derivative. Okay. So what do we do? Iteration is x minus fx is this thing, x power plus 4 minus x power 4 plus x minus 4 over its derivative. Now its derivative is 4x cubed plus 1. Now -4 has 0 derivative. So this is the, then choose our h1. Now the choice is insignificant as long as it's a reasonable choice. Okay. So for instance, we choose x1 to be 1, or you choose any other choice from 0 to 2. And then you get h2 be plug in h1. Okay. And then you get the number x2, and then you plug in x2 to the h, then you get h3. Then you plug in h3 to h, you get h4, or you get x4, etc., etc. So you get a sequence, a bunch of numbers. These numbers, the sequence of numbers should converges to a certain number. Now, it's of course, if you do this by hand, you can do it by hand, but it's really tedious. So we just give this tedious work to using algebra package. So let's just use algebra package to compute it. Okay, let's use algebra package. Okay. So our function f is x power 4 plus x minus 4. Then we define our h. So gx, we first find the derivative. Let g be derivative of f. Okay. So you can check, use power rule, you get a gx. Then we define our hx to be x minus fx over its derivative. Here its derivative of f is g. Okay. Then you get h. Okay. Our initial value x1 to be choose 1 for instance, choose 1. Okay. Okay, then we do a loop. We plug in x1 to h, and then we plug in x1 to h, plug in x2. So we get x2, plug in x2 to h. So this is actually a loop. So we don't actually need to use this variable x2, x3 is too many variables. So we only use the x1 variable. So the new output, we will rename it to be x1 again. Although in theory we should use x2. So here, this is the usual way that we use computer loop. Okay, to programming loop. Okay, so for I in let's see, for I in range 1 to 10. So here, I is the number of iteration. So we just do 10 times of iteration. Actually, you will see it converts really fast. You don't need to do that many times usually. 10 times is really good. And then we plug in. So we compute each. Okay, plugging x1 into each. The output is x2, but we name it to be x1. We renew x1 to be x2. Okay, so the x1 new value will be x2. And then we will put this x1, this value again, to this h1. So do this so that you get a loop. Okay, so you get a loop. So do the results, plug in h, so you get x2. And then you put it to be x1. And then you plug into this h again. Okay, so you get x3. And then you plug in this x3, you name this x3 to be x1. And then you plug into this function h again. So that you get it again and again. You get it 10 times, run 10 times. So you get a loop. Any questions? Okay, then what you do is you print your number of a loop. Print the number of iteration and print the output xy. Okay, so that you can do you see. Oh, sorry. Let's do it to be real numbers. Let's just do the real numbers. Otherwise, you get a bunch of ugly rational numbers. Okay, you get a okay. 1.1. Okay, so you see after several times of iterations, then the x value, you see it converges to certain number.
You plug x into the function.
Yes, plugging x to the function.
So from 1 to 10.
1 to 10 is the time of iteration. This is the first line is actually gives you x2. Okay, the first output number 1 gives you x2. Okay, now once you get x2, this is x2. You plug in to the function h. So this actually gives you x3. This gives you x4. This gives you x5. This gives you x6. Okay, you see from 5, 6, 7, 8, 9, the numbers does not change. It's stable. It's stable. Okay, it still change a little bit, but it's it's the real number. We only we only take finite number of digits. Okay, we only take a finite number of digits. So there are some tails we just forget. So it seems like it's stable. But here, if you do more precise computation, there should be more digits. Okay, it should be corrected to more digits. So you get a decimal approximation of the real number, the root. Okay. Okay. Let me copy this. Okay, so what we get is this loop, the output. Okay, the first time we get this is x2, this is x3, this is x4, etc., etc. So you see, after several times, you see the xn, they stabilize. Okay, they converges to a number. Now you check that. Okay, you plug in the numbers, you will find this is actually indeed a root. This is indeed a root. Okay, if you check that, if you plug in the numbers, you see this is really small. This is really small. Now this is really small. Now if you plug into more digits, you get an even smaller number. Okay, even smaller number. All right. Any questions? Any questions? Another question is, you may ask, okay, well, you choose your x1 to be 1 here. What happens if someone else choose another initial condition? Does the solution actually depend on the initial condition? Okay. Now, a good algorithm, you need to make sure a good algorithm doesn't depend on your initial condition too much. Okay, i.e., it should be robust. Okay, this is actually really important in computer science. You can design certain algorithm in mathematics, but in reality, you need to make your algorithm robust. Okay, because in reality, we always have error term, fluctuation, etc., etc. Okay, so that your algorithm should be robust. Otherwise, that can be disaster. It can fail. Okay, so actually, Newton method is actually a robust algorithm. I.e., if you choose your initial value, you know, here if you choose it to be 1, let's choose to be 1.5. Let's choose x1 to be 1.5. Let's see if we still get the same result. Okay, let's choose choose x1 to be okay. Then let's do this program again. And let's see if we get the same result, 1.2837. Okay, let's just check. You see, only the first several terms differs. Okay, the first several terms differs. And then finally, you see, again, we get our answer 1.283781, etc., etc. So this algorithm is robust. So you can choose different initial condition. You can choose different initial condition, but it turns out you will get the same result most time. If the function you did is, if the function you are dealing with is not too bizarre. Okay, so you see, we get a, so this is the initial condition. Choose initial condition. Choose initial condition. Choose initial condition x1 to be 1.5. Okay, you see, only the first several iteration we get different answer. But then finally, we at the end of the story, at the end of the loop, the iteration, then we get the same answer. You see, from 5, 6, 7, 8, 9, we get the same result. Okay. Okay. Now, if you the numerical evidence is really convincing. If you choose, not choose 1, you choose x1 to be, you choose any number, reasonable number from 0 to 2. Let's choose 0.5. Okay, let's choose it. Okay, and then you do this loop again. Do this loop again. Again, only the first several terms differs. Only the first several iterations differs. Then finally, you see this is really stable. Okay. Now let's choose another. Okay, you see, we choose our initial condition x1 to be 0.5. So choose. So our iteration, the first time we get 2.7. If we choose 1.5, the first time we get 1.3. But finally, at the end of the loop, you see we get the same result. Okay, 1.28, 1.28, 7.3, 37, etc., etc. So Newton method is actually really robust, really robust. Okay. Let's see more examples. Let's see more examples. Okay, let's see this example. More examples.
So you can choose.
Let's see. Okay, let's see this example. fx. Example. fx is sine x. Sorry. So solve this solution. Sine x equals x squared. Find its positive. Find its positive root. Find its positive root. First of all, we have a trivial root. We have a trivial root. You can see we actually have a trivial root. What is a trivial root? What is a trivial root? A trivial root is actually x equals 0. Okay, so we let construct our function f(x) to be the left side subject the right side, sine x minus x squared. You check f0 is actually 0. Okay, check. This is very easy. Sine 0 is 0. Minus 0 squared, this is 0 minus 0, which is 0. Okay, then now when x is positive, so now you check f derivative. F derivative, you get a sine derivative, cosine x squared, you get a 2x. So f derivative at 0 is cosine 0 minus 2 times 0, which is y minus 0, which is y. Positive. Then the function is increasing. Okay, by increasing decreasing test, the function f is increasing. So you can actually, it start from 0, if it's 0, the function is 0. And then it's increases. Now, when it decreases, if x is big, then it decreases. Cosine, if x is it decreases finally. At 1/2, it certainly decreases because cosine x minus x is a negative. Okay, if x is positive greater than 1/2, twice x will be greater than 1. So if x greater than 1/2, it certainly decreases. Actually, if as long as it should decrease before 1/2. So at 1, you check when x value is x coordinate, is y coordinate. If you check f value at 1, function value at 1, you see, then what you get is sine y minus 1. Sine y minus y squared with sine y minus 1. Remember, sine value is bounded by 1. So sine y is not equal to 1. So it's bounded by 1. So it's less than 0. Less than 0. So we can conclude. So there should be there should be a root. So that by f is continuous, so fx is continuous. So we can use continuity, continuous. So it's continuous. So fx is continuous. Then by the intermediate value theorem. Intermediate value theorem. There exists a root. A root x0 in from 0 to 1. Okay, 0 is a trivial root. So we find a positive root from 0 to 1. So we use Newton's algorithm, Newton method. What we do is here, now here, first of all, sine x equals x squared is just transcendental. You don't expect you can solve it by algebra. Solve it by algebra. Okay. So what we do is we use the following. Okay. We use the following. Okay, we use the following. Then what we do is the following. So hx is x minus fx over f derivative. So here fx is sine x minus x squared. Then f derivative, you use differentiation rules. F derivative is sine, you get a cosine. X squared, you get a 2x. Okay. So hx is, oh, sorry. Sine x minus x squared over cosine x minus twice x. Then we do iteration. Any questions? Any questions? Okay. Okay. Now we choose our initial value. We choose our initial value from 0 to 1. From 0 to 1. From 0 to 1. Now a reasonable from 0 to 1. A reasonable initial value is x1 to be 1/2. So this is just a reasonable choice. You can choose 0.7, 0.8. It doesn't matter as long as it's not too too big.
Why should
So then we do the iteration. So then we plug in x2 to be hx1, x3 to be hx2, etc., etc. So you get an iteration of the sequence. Okay, so let's do it by computer package. Okay, our function fx is sine x minus x squared. Okay, so gx is f derivative. Okay, then what we do is we define hx to be x minus fx over its derivative gx. Okay, we choose our initial value x1 to be 0.5, 1/2. And then we do the loop of iteration, for loop, okay? We did it by using our for loop. Okay, so this is the loop that we want to iterate. For I from 1 to 10, we do 10 times iteration or 9 times iteration. Then we compute the function value hx1, okay? RR here, the second line, this line, RR means real number, okay, just number. I want to avoid it to be, if you use it not equal, not RR, then actually you get a bunch of a rational number, huge number. It's really ugly to do that. So let's use a decimal expansion. It's easier to read. And then after you compute hx1, and then the function value just replace the x1. Replace the x1. Then you plot, then output x1, the new value. And then the next time of the iteration, I becomes increased by 1. Okay, I is the counting. Okay, we do the counting in this loop. Then, for the second iteration, the x1 is actually here. The x1 is x2 actually what we output last time. And then you put the x2 input in terms into the function h. Then you get x3. Then here the x3 we name it by x1. So this iteration again and again. So actually then we get all the iteration. Now you see after several times iteration, we the output stabilize at a 30 number. Let's see. It is stabilized at a 30 number. You can check this number is actually indeed a solution. Okay, you can check this indeed a solution. So here we choose x. So we get this. This one is x2. This is the x3. This is the x4, etc., etc. You see from x6, you see it is stabilized at 8 and 9. 8 and 9. Okay. If you do more times, it does not change. It's stabilized. Okay, now now you ask, can we choose another number, and if we get the same result, you can try to use another number and see if let's see. Okay, if you use another number, for instance, x1 to be 0.7. Actually, this should be better. This should be better. Why? Because here you see our root is 0.7. 8, 7. So 0.7 is close to our root. Okay. In general, if the function is not that too bizarre, if you choose a number close to the root, then it converts fast. Okay, it converts to fast. Converts fast. So if you choose this thing and then you do it again, then you see it converts faster than last time. It converts faster than last time. Okay. So Newton's method is actually robust algorithm. It's really robust. As long as you choose reasonable, the function is reasonable, the algorithm can be really robust. Okay. So here this we choose x1, choose x1 to be 0.7. Okay, more examples. Let's choose let's do this one. Let's do this. Example. Compute 7th root of 1,000. And you see, well, with a calculator, this is trivial. You can use a calculator to compute. Now, we will do it by Newton's method, and then illustrate how we actually use Newton's method, how it works. Okay, if we let the thing, let x0 to be this number, then you see we get x0 to the power 7 is 1,000. So x0 is a root. So if you move the terms, x0 to the power 7, subtract 1,000 is 0. Okay, so essentially we need to find a root to the equation, i.e. x0 is a solution, is a root of the equation x power 7 subtract 1,000, okay, equal to 0. Okay, now we find this root by Newton's method. Remember, Newton's method for this example is polynomial, okay? It's polynomial. What's the benefit of polynomial? Polynomial is algebraic, okay? Polynomial is algebraic. So algebraic thing we can compute by hand. Okay, now if you don't have a calculator, how do you compute 7th root of 1,000 by hand? How do you compute by hand? Well, you can use Newton's method. This example is algebraic, okay? Algebraic. So we choose, first of all, we can check x0 is from 2 to 5. Okay, you check 2 to the 7. What's the 2 to the 7? 2 to the 7 is 2 to the 3, 2 to the 7, 2 to the 3 times 2 to the power 4. So this is the 8 times 16. So this is of course less than 1,000. 5 to the 7. This is a 5 squared. 5 squared times 5 third. Now this is the 5 squared is 25 times 25. This is 125. So this is the 6. So times this of course greater than 1,000. So here x0 is from 2 to 5. So we choose our initial value to be x1 to be 3. Now here fx is, we want to find the root of fx. So we use Newton's method. Then what we do is we find f derivative is 7x power 7. Power 6. It decreased by 1. Then we define hx to be x subtract fx over f derivative. Okay, so this is the x subtract x power 7 minus 1,000 over 7x power 6. Now you see this is algebraic. Algebraic thing you can compute by hand. Okay, now in theory we can compute by hand, but in practice it's tedious work. So the tedious work, we human beings is really not good at tedious work. We better use computer package to do that. Okay. Okay, let's do it by a computer package. You see, okay, let's do it by siege. So fx, our fx is x power 7 minus 1,000. Okay, minus 1,000. Then we find its derivative gx to be f dot derivative. Okay, now you check gx is 7 times x to the power 6. So we get a gx. Then we get hx to be x minus fx over f derivative. Okay, gx. So let's check hx. Yes, hx is correct. Then we use the iteration. We choose our initial value to be 3, remember? X1 to be 3. Now we do the iteration, do this iteration, okay? Do the 10 times iteration. You see, let's do it. You see, this thing converts fast. So after several times of iteration, you get a really good approximation. Okay, now you check the number 2.68 to the power 7. To the power 7. You see this number to the power 7. You get 998. Okay, this really good approximation. Now if you do more digits, 6, 9. Let's use x1. Here x1 after iteration, you see you get the thing, 1,000. Okay. Now if you want several digits, let's see, 6, 8. Okay, you check. You get a 9.9, 999.999. Okay. Now if you add more digits, 5795. You get more 9s, and then you get more 9. And then if you get 2, 7, you see, you finally get more 9s. Okay, this is actually indeed a root. This is indeed a root. Okay. So this is the Newton method. Okay. So this is Newton method. So here we choose initial value x1 to be 3. Initial value to be 3. Now, of course, this algorithm computer converges fast. If you just compute this root to the number like 1 over 10,000, like 1 over 10,000 compute the root to this correctness, then you just actually need to compute 4 times of this algorithm. Then you are done. It's not that bad. You can compute by hand in theory, because here is algebraic. Okay, all right. More examples. Maybe one more example of Newton method. One more example. Let's do this example. Example. E to the x equal to 3 minus 2x. Now find correct to 6 decimal places. Find all roots. Find all its root. Find its root. Correct to 6 decimal places. This is okay. Okay, now once we have this equation, what we first do is we subtract the left by the right. So we let fx be, so we write it in this manner. So we write the left subtract the right to be 0, i.e. e to the x plus 2x minus 3 is 0. Okay, so we construct the function let fx. Okay, let fx to be e to the x plus e to the x plus 2x minus 3. Now, first of all, fx is continuous. And f derivative is positive. E to the x plus 2 is positive because e to the x is positive. So it's increasing. The function is increasing all the time. Increasing all the time. So it can only have one. If it has a root, then it can only have only one root. Okay. Now it's continuous. And then if we check f0, what is f0? F0 is e to the 0 plus 2 times 0 minus 3, which is the 1 plus 0 minus 3, which is negative 2. Now what is f1? f1 is e to the power 1 plus 2 times 1 minus 3. So it's e plus 2 minus 3, which is a e minus 1. Remember, e is decimal expansion. E is around 2.718, etc., etc. This is greater than 0. Okay, so we know it's increasing. So it's increasing all the time. So it's at 0 is negative 2, value is negative, at 1, when x is 1, then its value is positive. Okay, it's increasing. So we don't, it's concave up actually, concave up. So we should have a root. We should have a root, okay, at between 0 to 1. And we only have one root, okay? X0 is a unique root for this problem. Okay. Then we use Newton method. First of all, this is transcendental. E to the x is transcendental, so you don't expect you can easily solve it by algebra. Okay. So we use Newton method. We use Newton method. We choose our initial value x1. Choose x1 to be a reasonable number between 0 to 1. Let's see, choose 0.5. You can choose a different answer as long as it's reasonable. Then you should get the same result after several iterations. Okay, so we choose again our Hx to be x subtract fx over f derivative. Okay, now we already did our fx is e to the x plus 2x minus 3. And then f derivative is e to the x plus 2. Okay, so this is actually the function that we iterate. Now it's hard to, this one is, we don't compute by hand. It's tedious work. Now iteration, we use computer package to do that. Okay. Okay, now we define fx to be e to the x plus 2 times x minus 3. Okay, then we check, we find the derivative of f. So we get its derivative e to the x plus 2. Then we define our hx equals x subtract fx over its derivative, gx. So we get hx. Then we choose our iteration x1 to be c 0.5. Then we do our iteration. Okay, this is the iteration that we want. For I from 1 to 10, I control the iteration, the number of iterations. We do 9 times iterations. then if you plug in the package, now you see it converts really fast. Okay, so this Newton method. Okay, so which now you may ask, well, why choose 0.5? Why we choose 0.5? Now, as long as you choose some reasonable number, you should get the same result after several times iteration. For instance, if we start from x1 to be 0.7, okay, and then do this again, you see? Only the first several iterations are different, and then finally, then we should get the same answer, okay? i.e., this algorithm is robust. Now we choose, if we choose x1 to be 0.7, the following data is what we get. Only the first several iteration differs. Then finally we should get the same result, converge it to the same result. Okay. 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 Any questions with Newton's method? Okay. Now you should be able to compute solutions to certain equations. Use Newton method. Use numerical thing.
So you can choose.
Okay. All right. Now let's start a new section.
Really?
Okay. Let's start a new section. Okay. Now let's start a new section. Arc length. Arc length, we use integral thing to find arc length of a certain curve. So let me add it.
Oh.
Question? Okay, let's inner lines. Okay, all right. Okay, so questions? Chapter 1. Chapter 8, applications of integration. So this is actually arc length. Arc length. Now, for curves, find arc length of curves is actually really old topic. When calculus was invented, then people use calculus integrations try to find arc length of curves. Then there are many curves. You can write down any curves, and then you compute its arc length. And then this turns out to be, mathematicians often challenge each other with this arc length problem. I write a curve, and then finds arc length and give it to you. Can you find this arc length? So this kind of arc length problem in the early history of calculus. So it says this: suppose suppose we have a function y equals fx. To be a reasonable function, be a nice curve. Question is, how do we find the length of the curve? Question: what is the length? Length of the curve. So suppose we have a reasonable function y equals fx. Okay, A to B. This is A. Now this is B. This is B. Now, what's the length of the curve? From A to B. Okay, so this is x, this is y equal fx. Okay. The idea is this is, now first of all, we don't have a formula right now to find this curve. Then the idea is we locally approximate an arc by a straight line. Okay, we use straight line. For straight line, we can easily define the length. Okay, the length. Okay, you can measure it by a ruler. Okay, so idea. We use tangent line to approximate. We approximate locally. Approximate the arc by a ruler, by a straight line. And sum them together and have good control. And the hope is you should have, for reasonable curve, we should have a control of the error term. Okay, we should have a control of the error term. This is why we assume the curve should be nice. Okay, in theory, you can have really bizarre curve such that you can the length can be arbitrary. The length you cannot find its length. Okay, you cannot find its length. The curve exists, is well defined, but its length is not. You cannot find its length. It's infinity. The length can be infinity. So okay, and find locally approximated by straight lines, by straight line, and sum these local lengths together, and sum local length, local pieces, some local length together, and hope you have good control of the error term. Okay, so if we let so first of all, we let Sx to be the arc length function. Suppose it exists. Let Sx denote the arc length function. Arc length of the curve. Arc length of the curve. Y equal fx from e to x, from e to x, from e to x. Okay, from e to x. Okay. All right. Now, suppose this is x. The arc length will be e to x. Okay, e to x of this thing. Okay, first of all, we have very easy observation is S A. We start from A, end at A. No, we only get a point. Now we define a point has length 0. Okay, this is 0, length 0. Next, we find, now if we can find the derivative of S. So Sx is the function of x. So if we can find S derivative, then we can use any derivative to solve S. Now, okay, find ds dx, derivative of S with respect to x. Okay, now we use local approximation. So suppose this is the SA. Suppose this is A, this is A. Now this is the x. This is A. So suppose we find its derivative direct x. Now we use straight line to approximate this arc length. Now this is a third one. Okay, so here if we use this this line, straight line, to approximate the thing. So for the straight line, we can find by arc length, we can find the line of the hypotenuse. The hypotenuse has length. So we can use this third x. Third x is the arc. Okay, third x is this arc. Okay, this arc. Third x has arc length third x. We approximated third x by the straight line, the hypotenuse, which is by third x squared plus third y squared. Okay. Okay. Now you may ask, well, what's the difference? What's the error term? It turns out, fact, this actually the right side square root x squared plus square root third y squared turns out to be the main part. Turns out to be the main part of this approximation. Okay, so third x turns out to be the thing, the difference, the error term. If you do this thing, subtract this thing to be higher order of x. Okay, order greater equal than 2. Order greater equal than 2. So this is higher order. If you take limit in the Riemann sum, then this thing, the error term will vanishes. Okay, so here s equals, so this is fact. Fact s equal to the sum of third x, okay, third xi. Okay, this x equal to the sum. You can approximate by the thing, Riemann sum. Okay, if you factor out third x, so this be 1 plus third y over third x squared. Okay, it turns out you can find the differential of arc length. So this, if you take a limit, you get the differential third x upper 0. So this you get the arc length differential. Okay, using Riemann sum, if you take a limit, the thing third x upper 0 and sum that together, what you finally get is s is it will be 1 plus integrated thing third y over third x approaches derivative. Okay, so you get arc length differential. So we get arc length differential. So this is arc length differential. Or you call it a length element. Arc length element. Okay. And then if you find an antiderivative to cancel d, okay, then you get this definite integral to cancel d. Okay. Okay. Now it turns out the proof can be really tedious. The proof is tedious. So we will avoid the proof. If you're interested, you can try to write down a proof. Use Mean-Value theorem. Okay, let's see some examples. Example. X squared plus y squared equals 1. And y greater equal than 0. So this is actually the upper half semicircle. A semicircle. The unit circle. 1, -1. This is the 1. Of course, we already know its answer. The answer, the arc length of a circle is 2 pi r, but actually it's half of a circle. So it's the length, arc length is pi. So we should know the answer should be pi. Now you check if you solve y squared is y minus x squared. If you take positive root, y is positive here, is you get the thing. And then you find this derivative, dy over dx. Dy over dx, then what do you get? Use, it's very easy. Use differentiation rules, you get the thing. And then dy over dx squared. So remember arc length, the squared will be, you take square, negative x over the thing squared. Then the square cancels square root, so denominator is y minus x squared, numerator is x squared. Then arc length element ds is 1 plus dy over dx squared dx. Okay, so this will be 1 plus x squared over 1 minus x squared dx. Okay, then you do the algebra. So you come down 1 minus x squared, 1 minus x squared plus x squared. Take a square root dx. So this will be x squared cancel x squared. So this will be 1 over the thing dx. So this turns out to be this is 1 over square root 1 minus x squared dx. Okay, so s will be negative 1 to 1 ds. Sorry, it should be this differential form, x from the thing. Okay, now you can use fundamental theorem of calculus. So this actually improper integral actually. So if you do the improper integral, so this is arc length, arc sine x. You use antiderivative formula, you get arc sine, negative 1 to 1, negative 1 to 1. And then arc sine of 1, you get arc minus arc sine negative 1. Arc sine of 1, you get pi over 2. Arc negative 1, arc sine negative 1, you get a negative pi over 2. So it's pi over 2 plus pi over 2. So you get a, finally you get an answer pi. No surprise. No surprise. Okay. Okay, more examples. More examples. So y equal x squared. The curve is from 0 to 1. Find its arc length. Find its arc length. Okay. Arc length. Y equal x squared, 0 to 1. Okay, 0 to 1. This is the 1, 0. This is the 1. Okay. Y equal x squared. Find this arc length, 0 to 1. Now we use arc length for differential. So y prime dy over dx. Then we got a 2x. Okay. So ds is 1 plus dy over dx squared dx. So this will be 1 plus 2x squared dx. Okay. So then what we do is s will be x from 0 to 1. And then we integrate the thing 1 plus 4x squared dx. Okay. Now this we get a definite integral. Now we use the technique to deal with we use integration technique to compute this integral. Okay. Remember we use substitution here. What substitution do we use? We have this, a squared plus x squared, x squared minus a squared, a squared minus x squared. So we use trig substitution here. We let x be 1/2 tangent theta. You can check according to which case what substitution that we use. In this case, we let x be tangent theta. Then dx will be 1/2 secant squared theta d theta. And then this thing will becomes 1 plus 4x squared. This will be 1 plus 4 times a quarter y½ times theta squared. So this will be 1 plus tangent squared. 1 plus tangent squared gives us secant squared. So this secant squared. Now secant theta is positive. We get secant theta here. Okay. So we finally switch the thing. So so essentially we need a computer secant theta times 1/2 secant theta squared d theta. Okay, this is 1/2 secant theta cube d theta. Check the lecture notes that we did in this part. Okay, we computed the secant theta to the cube antiderivative. Okay, if you remember. So then what we get is 1/2. If you check your notes, then what you get is secant theta times theta plus ln secant theta times theta. So this actually all the power of secant. It turns out to be the most tedious case when we talk about the tangent secant integral. Okay. Okay. Now here theta, where does theta from? Okay, so tangent theta is 2x. Tangent theta is 2x. X is from 0. If x 0, then tangent theta is 0. Secant theta is 1. Okay, if x is 1, then tangent theta is 2. Secant theta is square root of 1 plus tangent squared theta. So this is 1 plus 2 squared. So this is root 5. Okay. So you plug in when x is 0. X 0, everything is tangent theta is 0. So you get a quarter. So original integral will be I don't want to copy it again. So s will be, let's use just s. S will be plugging when x 0, when x is 1, tangent theta is 1. So you plug in tangent theta to be 2, secant theta to be root 5. So it's 1/2 times 1/2, you get a quarter. Okay, 1/2 times 1/2, you get a quarter. So secant theta is root 5, tangent theta is 2, plus ln tangent secant theta is root 5. You plug in, use Newton-Leibniz formula. Tangent theta is 2. Okay, so this gives us the value when x is 1. Subtract when x is 0. When x 0, then you see tangent theta is 0. This is the 1 times 0 plus ln 1 plus 0. This part turns out to be 0. Finally, then what we get is this is a quarter to root 5 plus ln root 5 plus 2. Okay, then we are done. Then we are done. Okay. We have 5 minutes. Okay, 5 minutes. Then let me maybe just quickly start a topic. And then we cannot finish this topic now. Of course, this is a big topic. So we work out arc length of a circle. That's easy. It's really easy. Now another question is arc length of an ellipse. Arc length of an ellipse. Remember, an ellipse, a circle is a special kind of ellipse. Okay, special case of ellipse. Now we find the circle. Now how do we find an ellipse? Arc length of ellipse. So in its general form, okay, then we get an ellipse. Okay, so this is an ellipse, more or less like an ellipse. This is a x, y part and length y part, the intersection is b and negative b. Okay, so this is y. Okay, if a equal to b, then we get a circle. Okay, this problem, arc length of an ellipse, it turns out to be a really classical problem in mathematics. Okay, now of course we have a general formula for arc length, so we can set up the formula, set up the integral. Now, actually, how to evaluate this definite integral turns out to be a classical problem. It puzzled people a long time. Actually, in the for a century, in the 19th century, actually many research is related with this topic, arc length of this ellipse. The integral of this ellipse, arc length of ellipse, is called elliptic integral, elliptic functions, right? Elliptic integrals. So if you solve the thing, you get a y squared over b squared is y minus a squared x squared. Solve y in terms of x. Then you get y squared is b squared minus y minus that thing. Okay, then you differentiate, use implicit differentiation. 2y dy is 2b squared over a squared x dx. 2x dx. Sorry, 2 we already get it. 2. Then actually you get dy over dx. Then you get a dy over dx. Oops. Then you get a dy over dx, which is negative b squared over a squared of y. Okay. Use implicit differentiation. Okay, then you can set up, okay, ds, which is y plus dy over dx squared times dx. So this will be 1 plus, plug in dy over dx, negative b squared x over a squared of y squared dx. Okay, so you can actually find s twice because it has two pieces. Okay, the upper half and the lower half. Okay, now if you substitute the y squared in terms of x, then you get the class. Then you get finally. Okay, finally. What you get is you substitute y squared. Substitute y squared by the thing b squared y minus x squared over a squared. Substitute here, then you get a one over function. Then this turns out to be what you finally, then you need to evaluate this integral. Dx. Okay, this turns out to be a classical problem that puzzled people many years. Okay, of course, in the 19th century, many people devoted their research on this topic, solve this thing. The conclusion is we cannot find it elementary function by this. However, this turns out to be a really important problem in mathematics. Okay, really important. It's it opened the door to a huge, beautiful mathematics. Okay, beautiful elliptic functions. elliptic functions and elliptic integrals. Now this elliptic comes from the ellipse. Okay. Now of course, there are many books devoted to this topic, and they think we cannot finish in 5 minutes. It takes people more than a century to do this. Okay, maybe let me just stop here for today and continue on Wednesday.